Well, hello again, OT699. So we are now on our second week of hardware based around Arduinos for electronic prototyping. And this week we're going to be talking about sensors. So anytime you want an electronic device or a computer or any non-mechanical machine really to respond to the physical environment and the outside world, you'll need some sort of a sensor. And for many years, that was really the domain of engineers, some types of computer scientists. This is something that has only very recently become accessible to everyone. And so it's a pretty exciting time because you have within tens of dollars and not hundreds of dollars, the ability to really acquire sensor data and do things with that data in real time using little microcontrollers like the Arduino. So without further ado, I'll get into a PowerPoint presentation. It'll last for just a few slides, and then we're going to be spending most of this lecture on the actual Arduino code itself and how we can take in and process sensor data. That will be in a form that's a little bit different than a classic standard tutorial that you might find on an Arduino website, but I think it'll be worth it because by the end of this lecture, the goal is that you will have on your computers software that lets you use your Arduino as a legitimate data acquisition system that you can use for real-time display of data or for triggering parts of circuits, digital outputs that make buzzers and lights go off, things like that. So I'm going to share my PowerPoint screen now and get rid of myself. And here we go. All right, so I've divided it up roughly, as I said, into two basic parts. The first part's going to be more just some PowerPoint slides related to the concepts of sensors, how they work, what kinds of things you can do with them, especially in medical technology. And the second part is going to be making the Arduino sense the world and respond to it in some way. And that will be more on the Arduino programming code side of things rather than the PowerPoint side of things. I will put all of the screenshots of important blocks of code in the PowerPoint presentation though, so it may help to have the PowerPoint open or printed while watching the lecture. Of course, you can always use screenshots from the lecture if you need to, but you should have all the materials to create the same code that I'll be creating progressively over the course of the next hour or so. So let's start with where are sensors used? Okay, so that's a loaded question because they're used everywhere. So it's pretty much futile to attempt to narrow this down into 2 or 3 bullet points. Basically, any device that isn't purely mechanical and takes user input, is interactive, responds to or measures the physical world in any predefined way, has made use of a sensor. And we started learning a little bit about how the process of making electronic sensors works because we read the state of a tilt switch into a digital input on the Arduino. And you can think of a digital input pin on an Arduino as something like reading an analog channel. It's just a very, very low resolution one. It can only read 2 values, high or low, right? So because reading that digital pin is just high or low, you can't really do much more than turn things on and off. But in many cases, you'd want to know a continuous measurement, something like temperature, the rotation angle, how much force is being applied to some sensor, distance from some sensor to the wall, things like that. And many medical devices also need the ability to transduce some form of physical quantity into a voltage to be read as well. And so to give you kind of an overview of what some of the medical devices would be, I've got a kind of partial list on the side here. All the things with E in the beginning of them, like EMG and EEG. That's electromyography for muscle activity, electroencephalography for brain activity recorded from the scalp. You can also use sensors for eye tracking. These are basically light sensors that are tracking where your pupils are. You can also sense muscle activity around the eyes. That would be EOG. I didn't put it on this. There's also heart rate, the classic ECG. If you want to know something about how much sweat is on somebody's skin, because that correlates with their autonomic nervous system state, their sympathetic activity, basically how aroused or excited they are. You can look at things like skin conductance and pupil dilation. Again, these are some fairly basic sensors being used for very specific purposes. You can have respiration sensors. Some of them sense the stretch of a belt that you put around your chest. Some of them are based on temperature of the air coming out of your nose. There's skin temperature as well. You can train people to increase blood flow to a region, for example, by giving them biofeedback of their skin's temperature. There's, of course, audio, so voice feedback. That's a classic one. Almost every computer has a microphone and a speaker. There's body movements of all kinds for many purposes. You can get force produced by, say, grip in a rehabilitation setting. You may use force to train a muscle's strength. And of course, there's lots of behavioral choices and cognitive tasks that require various push buttons and things like that. And you can consider that in the category of physical things being sensed as well. If you put a particular item down on a table, knowing that it hit the table at this exact moment, that kind of thing. And when you're looking into acquiring any of this data, there are a couple of considerations. One, of course, is the sensor itself, and we'll get into that a little bit more in future slides. But then you also have to think about the hardware. How do you get the physical pieces parts to maximize the signal that you're looking for and also minimize noise that might be associated with collecting that data? You also need to think about the resolution of the analog to digital conversion. Every one of these sensors at some point or another is giving a system like an Arduino a voltage. You have to turn that into digital bits, binary zeros and ones at some point for it to be put into a computer and stored and used. And the resolution says whether you can break up a 5-volt range into 2 parts, high or low, or 20,000 parts if you really need very fine precision. There's also the signal amplification and processing. Many signals produce only very, very weak voltages, like millivolts. So in order to detect that, you usually need to ramp that up and amplify it. Also, there's some filtering and smoothing involved, and we'll get into that in a little bit as well. That will basically prepare the data for its end use. And it may be that you want to display a signal and you want it to be a nice smooth trace. So you would have to take a couple of samples of your signal and average those together over time so that it creates a more smooth trace with less noise. And of course, that also plays into this next one, display and or utilization and eventual storage of this data. Now, a lot of these can be done cheaply in various pieces parts. So you can do something like buy a sensor for very cheap, but then to acquire that data into a good acquisition system is going to start costing money. And a lot of people don't focus on selling software for any acquisition system or acquisition systems for any sensor or sensors for any acquisition system and software combination. Usually what ends up happening is you have some company that gives you the whole package. For example, with EMG, you might purchase a system for $10,000 or $20,000 that will give you nice wireless sensors that you can stick onto the skin to sense muscle activity, but it will also come with your acquisition system. It'll also come with the software. The software has to talk to those particular sensors, and it's generally inconvenient to start mixing and matching other people's sensors with this system and software. So you have to be a little bit aware that a lot of the price in the real world for sensors is based on the fact that these companies aren't giving you just straight hardware and letting you do any of the internal workings of the computer yourself. They're giving you the full package to make it nice and easy. But if you know a little bit about, say, Arduinos, for example, and you can go to Amazon and buy little $30 MyoWare EMG sensors, you can actually get most of the same functionality for rehabilitation purposes, at least, as a very expensive system for maybe like $100. It just means that you have to put together the software. You have to control the acquisition process. You have to, wire things together yourself. If you can do that, you can take the price down by orders of magnitude for most purposes. And just to talk a little bit about what EMG might be used for, it can provide awareness of muscle tension, obviously, but also it can be used to detect responses to other kinds of perturbations that you might want to apply to somebody to test things. Like, for example, if you startle somebody with a loud noise, the EMG response to that startle, like the neck muscles tightening, for example, can tell you something about the brainstem, and responses to electrical stimulation of a nerve or a tendon can tell you something about proprioception, you know, how basically the electric version of a knee-jerk reflex. The response to a pulse of magnetic stimulation at the head, that's transcranial magnetic stimulation, that can tell you something about corticospinal excitability, and it might be useful to track changes in the nervous system after stroke and with recovery. The type of muscle coordination patterns that emerge after something like stroke are also of interest. So getting lots of sensors on lots of muscles and looking at patterns of activation when people try to do functional tasks like reach forward has been extremely helpful in the research world. And you can also detect brainwaves. A lot of people don't think of EMG as a brainwave, but with a little bit of processing, what you can actually do is use the muscle signal as a kind of amplifier for the brain input going to the muscles. And so in many ways, you can use EEG and EMG almost using the same vocabulary. The same brain oscillations go from the scalp down to the muscles, and you can detect them there. So we just talked a little bit about EEG. EEG is used for testing sensory systems. For example, you can poke somebody and see how the brain responds. You just have to poke them repeatedly and average the responses. But those are called evoked potentials. And you can poke them physically, or you can use a loud noise. You can use light for visual evoked potentials, all kinds of things like that. They use this for, say, multiple sclerosis, where the timing of when the brain responds to a light is different in different stages of that condition. You can look at a lot of basic research questions. But again, if you want a nice fancy EEG system, you're probably going with 100,000. Well, $100 would be 1 or 2 channels. If you wanted a full set, a full scalp of channels that are all very clean and can be used for research and are FDA approved for various medical conditions, now we're talking maybe $30,000. But again, it's just a voltage sensor. And that's not expensive technology. It's all the extras, the stuff that a lot of these companies are assuming nobody knows how to do, and that's generally true. But it won't be for you. There's also eye tracking. They are little sensors that look at where your pupils are, and by tracking the pupils and doing a little bit of math to calibrate, you can see where people are looking on a screen. That's big in the world of, say, let's say autism research, where scan paths, where people are looking in a visual scene or a social scene, for example, are important. Do people look at the eyes of other people? Do they share attention? If somebody across from you looks over there, do you also look over there? That kind of thing can be quantified scientifically with these eye tracking sensors. You can also do some vestibular testing. There's the oculomotor reflex test. Basically, you spin somebody in a chair and then stop, and then see how long it takes before their eyes stop moving back and forth. There's all kinds of things you can do. And again, the sensor itself, fairly simple. It's all the other stuff you do with it that's complicated. Skin conductance I had mentioned before. That's basically how much resistance is in your skin. And your resistance changes if you have more water in your skin, like because of sweat. And when you get nervous, you sweat. And it's all very subtle, but you can, with an amplifier and a little device for somewhere between $100 and $3,000, you can basically see a trace of how nervous somebody is at any moment in time. And that's used in lie detector tests. It's not really detecting lying at all, incidentally, so don't use it in court too often. But general sympathetic arousal. There's also many, many sensors for movement and position, joint angles, acceleration. These can go anywhere from $50 to $20,000, and they are all over the place now, especially because game systems have started to use them, especially virtual reality systems are looking at 3D motion as game controlling signals now. And you can also use it more for rehabilitation purposes. If you just want to, say, have somebody increase the angle of wrist extension, you can try to give them some sort of gamified feedback of that. But again, a lot of these systems, if they're not commercial game systems, are attached to research grade systems and can be very expensive. So that's just kind of an overview of some of the more popular medical sensors that might be relevant. But now it's probably good to pause and talk a little bit about differences between the sensors under the hood. So sensors that measure things like EEG or EMG or ECG, these are biopotentials. You're measuring voltage directly. And essentially, you're not converting energy into different forms. You're taking a small voltage that you pick up on the skin and then amplifying it and feeding it over to your voltage sensing analog input channel in the Arduino or whatever you happen to be using for data acquisition. So it's voltage to voltage. There are other sensors, usually in this case called transducers, that take one form of energy and turn it into voltage. So one of the most common ones is that you have a sensor that is essentially just a resistor, but it just so happens that that resistor changes its resistance based on some property of the physical world. So for example, a photoresistor that we worked with last week is going to be a resistor that changes its resistance depending on how much light hits it. There's also strain gauges and things that sense mechanical deformation. Basically, if you take one of these little sensors that I guess you like a strain gauge, for example, and you try to bend it, it will change its resistance to electricity depending on how much you're actually bending it. And so that can be on a microscopic scale. These are just resistors that are fancy. And so using Ohm's law and V equals IR, you can get a voltage signal out of a variable resistor. And we'll work with that a little bit later. There's also some mechanical, there's some materials that will translate mechanical deformation into electrical energy. And these are called piezoelectric. So this is the basis of many buzzers, as well as some force sensors, audio pickups, things like that. One of the nice things about piezoelectric devices is that they work in both directions. So if you take a piezoelectric material and you mechanically deform it, it produces electricity that you can sense. But at the same time, you can also send electricity to a piezoelectric material and it will mechanically deform. And so that's why you can use these things as speakers to make tones. There's also photovoltaic sensors, which are basically little solar cells. They take light and turn them directly into electricity. Some important commonalities between the different sensors, and no matter what your sensor is, this progression from getting the voltage to having the data in your computer is going to be strikingly similar no matter what type of data you're collecting. First, of course, you need the sensor to provide you with a voltage signal, so you need to know what the range of your sensor is. Is it going to give you from 0 to 1 volts or -5 to +5 volts? So that's the first consideration, is what is the sensor outputting. The next is going to be that you need to feed that voltage into an analog to digital converter, and you have to do so at a predictable rate. A lot of these signals can be sensed very quickly, but the equipment for taking in that information there's no such thing as continuous data in a computer. It's all samples. It's all continuous sampling, I should say. To slow that process down a little bit, it's more like the computer is saying, what is the sensor value now? And then waiting, getting a response, storing that, and then saying, okay, what is the sensor value now? And it samples the real world that way. And it can do that very fast, but there's no such thing as a continuous signal. It's all discrete. It's all sample by sample. And so in order to interpret data from sensors, you need to set up a sampling procedure where you know exactly how often you're getting a new value from that sensor. So I could name number 2 sampling, essentially, but it falls into the whole process of digital to analog conversion. Now, I put 2 bullet points under number 2 there. You sometimes do need to amplify your signal and reduce noise in your signal with hardware. We don't have the parts to do that with the Arduino kits that we're working with, so we're not going to be doing that part. But sometimes you know a signal is going to contain some sort of noise, and with a couple of electrical components, you can just pass the signal that you're getting from your sensor through a couple of these little parts, a capacitor and a resistor, and then what ends up being detected by your analog to digital converter is now noise-free because those components have already smoothed out some of that stuff. We won't be building those circuits, and those are actually fairly specific to individual devices anyways. So what you're getting today is going to be much more general purpose. Once the digitized data is in a microcontroller or a computer, then you need to do something with that data. Usually you need to know what the units of the measurement you're taking are. So just taking data into a digital port, or an analog to digital converter, I should say, gives you some number between 0 and 1023. You have to then convert that to volts, and then convert volts to, say, distance or force or something useful. We'll get into that process a little bit as well. And so you'll be converting the distance sensors data into actual centimeters today. Then finally, the data has to be used for something, and use can mean lots of different things. One of the common things to do is to just display it in real time so that you can watch your signal changing, going up and down. The other thing that we're going to try to do today is use that signal to control other elements in a circuit. So if the value of the sensor goes below a certain point, make a buzzer and a light go as an alarm. We'll be doing that a bit later. So I had kind of mentioned the analog to digital conversion process, and before we get into how to actually do that, I just want to smooth one thing over a little bit. So first, last week we built an example where we were sensing a digital pin, and sensing that digital pin gave us a value of high or low, which was either 0 or 5 volts. Analog inputs work similar to this, except they have the better resolution. A digital input is essentially an analog input with 1-bit resolution. Resolution is something you can calculate by raising 2 to the power of whatever your bit resolution is, because there's 2 choices for each bit, 0 or 1, right? And so 1 bit would be 2 to the first values, and it breaks up 0 to 5 volt range into 2 values. So you get 0 or 5, or 0 or 1, high or low. That's all you get. But analog inputs, on the other hand, have, in this case, for our Arduino at least, 10-bit resolution. So what that means is that it's breaking up the 0 to 5 volt range of possible inputs into 2 raised to the 10th different values. So that would be a number between 0 and 1023. That's technically 1024 values, but because we're counting 0, the actual system will give you a number between 0 and 1023. And we'll use that as a starting point. And then by using that same circuit that we made last week and just making a few modifications to it, and then doing some software wizardry, we'll turn your Arduino into a fully functional analog data acquisition system. So before I switch over to code and the Arduino cam, this is just a review of what we built last week. So remember that this is a digital circuit here that we're looking at, and number 4 here was that tilt switch. We won't be modifying anything about the number 1, which was the buzzer, or number 2, which was the light. We won't be touching that at all. That will stay the same. As a quick review, when channel 13 is being turned to high, the electricity is traveling all the way through and back to ground, making an alarm sound. And we had turned that on and off with the tilt switch, which was being fed into digital input number 7. But now we're going to change the tilt switch and the acquisition of a digital input channel to a sensor and acquisition of an analog input. And that analog input is going to come from a potentiometer. The potentiometer is a little black dial that came in your kit. I don't think it's even labeled on the cover of the box for some reason, but it's in there. And it's maybe a little bit bigger, taller than, say, the buzzers. You have to be a little bit careful because this part that you squeeze and rotate can come out of the base if you're not careful, so keep it pushed in. A potentiometer is nothing more than a resistor that you can vary the resistance of based on, in this case, twisting it. The way it works is pretty simple. Let me get a pen out here and kind of trace. This squiggly line symbol here is the electrical symbol for a resistor. And so the way that a potentiometer works, whether it's in the form of a rotational dial or whether it's a slider, doesn't matter. It's the same concept. The electricity is going to start coming in from your VREF, that's your plus 5 volts, and it's going to travel through the wire, and then it's going to start hitting the resistor that's built into the potentiometer. And at some point, it's going to hit a fork in the road. It can either go down one path to your analog acquisition system, where it's just a wire going to your analog input 0, for example, or it can go further through more resistance to ground. And the symbol for ground is this thing. The electricity won't choose one or the other. It'll go part way to both. So if it turns out that your little wire going to output creates a fork in the road early on, then a lot more electricity is going to be going straight to your output than fighting through all of this resistance to get down to ground. And if you slide the thing way over to the other side, so now the fork in the road is basically almost at the complete end of the resistor, then the amount of electricity going to your analog acquisition system and to the ground is going to be the same, because the electricity faces no difference in its path from the ground to the analog acquisition. Now, that will make a lot more sense when we do it. Let me just erase all this. So one of the things that is nice about potentiometers is that it doesn't really matter which is the reference plus 5 volts and which is the ground. That just changes whether a larger value comes from turning the thing counterclockwise or clockwise. What you really do need to know about the potentiometer is that the middle pin, the middle little leg sticking out, that's the one that you're going to send into your analog input in the Arduino. So let's look at that real quick. The circuit diagram would look a little bit like this. So I've taken out the tilt switch, which was sitting up here, and now replaced it with a potentiometer. Now, the red wire shown here is going to go to column 40. It doesn't really matter which, but what does matter is that you attach column 40 to the plus 5 volt source on the analog side of the Arduino. And then the middle wire here, the black wire, is going to go to your ground. That's right next to the plus 5 volt on the analog side of the Arduino. And then the yellow, the middle pin, is going to end up traveling through, I think this is column 44. We're going to attach column 44 to A0 for the 0th analog input. And so it should look a little bit like, let me get my other camera going. Here we go. So it should look a little something like this. I can do this without all of the parts coming undone. That would be particularly good. Now you have to extend those little legs of the potentiometer using the female to male jumper cables, because it turns out this little dial, which is not really focusing extremely well here, but you can kind of see the silhouette of it at least. Those little legs don't fit very well into the holes of the breadboard, so it's kind of necessary to attach some wires to it. And those wires are going to be now nicely lined up like they were in the PowerPoint figure right here, from 40 to 42 to 44. And then those columns are attached all the way back here to the analog side of the Arduino. In the ground, the plus 5 volts, and the yellow one here is the analog input 0. So before getting into the actual actions of this particular circuit that we just made, there's an important distinction that needs to be made between everything we've been doing so far and what we're going to start doing now. Before, we've always been having the actions of the circuit run inside of this void setup. What I have here on the left is the blink sketch that you can get to from going to File, Examples, Basics, and Blink. And we worked with this a little bit last week. It was a very simple code in that the only thing you really do after all of these comments is tell the Arduino that you want pin 13 to be an output. And then in the void loop that runs repeatedly over and over again, you just turn that pin on, delay, which means go to sleep for 1,000 milliseconds, and then turn the thing off, and then go to sleep again for 1,000 milliseconds, and just repeat that constantly. Using delay in this way is easy to see what's going on. It's easy to write a little bit of code that makes a blinking light, but it kind of is impossible to expand beyond this, because the entire Arduino has to go to sleep every time there's a delay statement. You can't be sensing anything else in the meantime. You can't be doing anything else in the meantime. Whatever you might like to do inside your void loop is now totally paced by the fact that you have this one blinking light. And that's really not ideal. What would be much better is if you could keep the loop going at its normal rate. And remember that the void loop automatically iterates thousands of times per second. So you'd like to keep that going and then just keep track of time so that every, say, 1 second, a light turns on, and then if another second goes by, the light turns off, and do something like that. That way, in the meantime, you can be controlling other circuit elements, you can be listening into other devices as fast as the Arduino can do it, and you don't need to pace everything by this one blinking light. It turns out that there is a solution for this, and they've given kind of an example of this in what they call blink without delay. It's another example. If you go to File and Examples and you go to Digital, it's the very first example that you get. And we're not going to work with this code directly. I'm going to have you working with one that I've started, and then you just kind of add the middle pieces to it. But I'd like to point out what they're doing in order to make a light blink without using the delay function, because we're going to use it for our analog data acquisition. First and foremost, before any of the void setup or void loops, they set up a variable called interval, which specifies that they want 1,000 milliseconds, in this case, to be the interval between blinks. And they also specify something called previous millis. And the reason why they're calling it millis is because they're using a milliseconds function. This little red millis down here is the function that asks what is the current time right now in milliseconds. So right now they've just initialized a previous time as 0, but then, and here's the cool part, once you get into the void loop, the very first thing that you do is figure out what is the current time right now, like current computer time right now. And then there's an if statement. Everything else in the void loop is now inside this if statement. And what the if statement does is it says, if the current time right now, if the difference between the current time right now and the previous time this if statement was true is greater than some interval, then execute everything inside the loop. The very first statement within this if statement is to set previous millis to current millis. So basically, every time this if statement runs, because it was true, you'll make the previous milliseconds be the time that it ran. So let me just walk you through real quick what that would look like. If the void loop starts at 0 and goes along, it's going to set the time at 0. It's now time 0. The previous milliseconds from above was also time 0. That's not greater than 1,000. So the loop will pass over all of this completely. And it'll do it again and again until eventually you get to 1,000 and I guess because this is greater than equal, it will get to 1,000 milliseconds. And then all of a sudden, the current milliseconds is going to be equal, the current milliseconds minus the 0 from up above, the previous milliseconds being initialized. That difference is going to be equal to interval 1,000. So it's going to execute this next couple of lines. The very first thing it does is it sets the previous time to the current time. The reason why that's important is because now, after you've executed this code, the loop will start again. It'll get the current time, and what it will be subtracting is the current time right now minus the time at the last iteration, and that won't be greater than 1,000, not for another 1,000 iterations actually, or another 1,000 milliseconds worth of iterations. So this is a way to pace an entire block of code to only operate once every interval milliseconds. They used it to make a light blink at a constant rate. But if you think about it, the very first step in analog data acquisition is to set some sort of a sampling rate. This is how you set a sampling rate. It's just instead of using an interval of 1 second, you would use an interval more like a few milliseconds. And every single time the if statement reads true, instead of turning a light on and off, you're going to read your sensor. And as long as the stuff inside this loop can be executed fast enough, now you have a sensor being read at evenly paced, predefined time intervals, like a regular sampling rate. And that's how you can use a kind of cheapo microcontroller to do real data acquisition. So I'm going to close these two examples right now and go to a file that I've sent you called starter DAC. DAC stands for data acquisition. And this has a couple of features that I'm just going to go over first, and then we're going to start adding things progressively to this code and see how that works with some real devices or real sensors. So to start off, in the very beginning, I'm just defining a few sensor pins and a few variable names. Right now, I'm only going to have one analog input channel, so I'm saying integer sensor pin equals A0. A0 is the analog input channel. And I'm going to have a variable keep track of what that pin is reading at any given moment in time. I'm using float here because in the future, I plan on turning the sensor value into a voltage between 0 and 5. If I was happy with just some number between 0 and 1023, I would probably also call this int for integer. You only really need to know float and integer with the possible exception of unsigned long. All the rest of the possible formats you don't really need to know about. Unsigned long, however, is for the next block. That's for timekeeping. What is the previous time? What is the current time? And I set up a variable that's actually the difference between the previous and current time, just so it's a little easier to follow the code later. And also, I've set up an interval of 2,000. Now, in this case, I'm going to use a function called micros instead of millis. So now it's going to ask, what is the time right now in microseconds? That's going to be a little bit more accurate because I would like to set my loop timing up to be as close to a millisecond value as possible. And 2,000 microseconds is equal to 2 milliseconds, otherwise known as 500 times per second or 500 hertz. And that's pretty good for most sensors. Sometimes you need 1,000, sometimes you need far, far less than all of this, but 500 is something people use even for EEG, for example. So if we can get a nice sampling rate of 500 hertz, that would be a victory. The next thing down is going to be for actions of the program or math operations. The one main math operation that I've preset for you is the conversion from the analog value that gets read automatically to volts. All you do is you take that 0 to 1023 value and multiply it by 5 over 1023. Since that's kind of a common thing, I've given you this line. So now anytime we read analog input, we can just multiply it by this variable called convert to volts, and we've got volts out of it now. In the void setup, I only have one thing. The void setup is not right now going to set up any digital inputs or outputs. All it's going to do is tell the Arduino to communicate with the serial port. And that's going to be important because I want to show you what the Arduino is seeing on this computer that you're looking at right now. And in order to do that, data has to pass from the Arduino into my laptop through USB. So I'm using the command serial begin, and in the parentheses is a number called the baud rate, B-A-U-D. That's basically like a speed of communication in terms of bits per second. You don't really need to know the details. I've set this as a fairly fast value. If your computer seems to act slow or something, you can always set this down to 9600 or 115-200. For our purposes today, almost any of these will work, but the slower the rate that you have here, the more likely it is that you won't be able to have a very fast sampling rate being printed out for you in real time. In the void loop, I've preset just the timing of the loop for you, and everything else we're going to write now. Basically, I've got what is the current time, and then what's the difference between right now and the previous time that an if statement was executed. The if statement is right here, the same as before. This is exactly the same as the blink without delay, except I'm using current time and previous time instead of current millis and previous millis. That's it. And I've also used time check as a variable to make current time minus previous time a little bit quicker and easier to write and easier to follow. The real meat of the program is right here. Sensor value equals analog read sensor pin. And the sensor pin, remember, was defined up here as analog 0. It's just going to read the value, and right here, it's going to print it into the serial port. The serial.println is different from serial.print, and I'll get into that in a moment. But the serial.println means print this on a new line. And print this value in parentheses on a new line. It'll make a giant column of data, bottom to top of the screen. If I took out the ln, it would make one row and connect all of the data points left to right in one big, long, giant row. But if you had multiple values you wanted to see that way, you should separate them with commas. So the top two lines here, I can just uncomment them for a moment so you can kind of see what I'm talking about. This will print out the time it took to execute the loop, which should be about 2000 all the time, followed by a comma, and then it will print out the sensor value, all one row, and because of that ln, it will kind of hit enter and go to the next line down. So every 2 milliseconds, it's going to have those three things: the time it took the loop to run, a comma, and the sensor value. If I don't want to see the time it took to run the loop and at that particular, for what I'm doing, I can just comment those two out. And now it's only going to print the sensor value, just one per row in one big giant column. This is the framework that we're going to build everything else on. And I will plug my Arduino in now. And I have the potentiometer plugged in. It's going into analog input 0. And one of the very first things that I can do is go up to Tools, go to Serial Monitor, and it's going to start printing all this stuff out. Now I commented out, here, let me re-upload the sketch. I commented out the two print lines here since last we checked. So here's what it looks like. The analog input is reading a value of 426. The 0.00 is because I called it a float, but it's still just reading a number between 0 and 1023. If I pick up the, I just disconnected all the wires trying to pick it up. If I take the potentiometer and I plug it back in so it is connected and not giving random data, I can start to twist the little dial, and you can see the number is starting to go from 800 all the way down to 5, 400, 300, 200, 100, all the way down to 0. And that's just me twisting the dial around a little bit. If I wanted to also look at what the timing of each loop is, I can uncomment these 2 lines here, upload the sketch again, and if I go to the serial monitor, it's now going to give me that 2000, which is telling me, yes, every single time that it's printing, it took 2000 milliseconds, or it took 2 milliseconds or 2000 microseconds since the last time the loop ran. Make sure that you get the baud rate at the bottom of this window the same as what you put in your sketch. Otherwise, it will go a little bit crazy on you. And if it starts to slow down really bad, it may mean that your computer is working very hard. Right now, I've got a lot of things going on in the background and Zoom, so I'll just kind of close that for now. Hopefully, it won't crash my computer. Yeah, okay, we're good. Zoom is really, really hard to deal with for things that take a lot of computer inputs, outputs. It seems to hog all of the resources of the computer. In any case, once you close that, it should be fine. And I can go up to the one other way to view the data. I'm going to comment these out for now. And now I'm going to go back to Tools and Serial Plotter instead of Serial Monitor. And again, I forgot to re-upload the sketch after I commented those 2 lines out. When I go to Serial Plotter, it should be just 1 line now. It looks ugly because the y-axis scales to the data on the screen. So if I start to move the dial around a little bit without disconnecting it, because it's falling apart on me again. Let me just push all these pins in. Oops. Yeah, the potentiometer is a little bit finicky. I would suggest if you really like dials, get a real dial, not this little tiny thing. All right, so here we go. I am twisting the thing back and forth now. It's going between 0 and about, at the farthest end up, it's about 840 or so out of the 1023 possible. And the y-axis is being scaled to whatever you're seeing. So I'm twisting it up and down right now. If I just stopped, it'll really zoom in again. It's not really that noisy. It's just because the y-axis now goes from 280 to 285 instead of from 0 to 1000. This is now real-time plotting of sensor data. What I had been trying to show you or what I had accidentally showed you before was if you don't comment those 2 print lines out, it will also print or plot in this view a straight line at the time check, which is 2000. And if you try to visualize actual sensor data on a single axis with a giant straight line that says 2000 all the time, you won't be able to see what's going on in the sensor because the sensor data is all very much lower than 2000. So that's why it's just purely for visualization. It doesn't break anything. It doesn't blow anything up. It's just makes visualization better if when you're using serial plotter, you actually just plot sensor data. All right, so now we're going to do a few more fun things with this code. The first of which is going to be to convert the data from 0 to 1023 to actual volts using this convert to volts variable. So if I go down to the first blank section that I've left for you, we just have to write sensor value equals convert to volts times sensor value, because it was set up here between 0 and 1023. Now I'm going to multiply it by 5/1023 and get volts out of it. So if I upload that, I should now be able to see on the serial plotter a number between 0 and 5, and I do. Okay, so that is working well. I'll close that. The next thing to add is going to be a second layer that would be really good to add in most cases is going to be to make some element of the circuit turn on and off contingent upon what this dial is doing. So what I'm going to end up doing is copying a little bit of what we did last week and make kind of an alarm. If the value of this dial goes under 2 volts, then I'm going to set off the buzzer and the light. The first thing that we would need to do is go up and under the general input and output settings, add a few things. First, we need to make a output pin. So int output pin, I'll make that be pin 13 because that was the built-in that we had used before. Output pin. And under various other sections, we need to tell the Arduino that we're working with some digital data. So in the void setup, we also need to say there was a digital pin, and the pin mode of output pin is going to be output rather than input. Once we've got that, we need to give it, this is going to be some sort of a alarm that has a threshold, so we want to set a threshold. So up at the very top, we can define a threshold value or an alarm value. I'll put this under program actions or math. Float alarm value or alarm threshold. For now, I'll say it's 2 volts. And comment over there. All right. Now I've got everything set up so that within the void loop, I can go down and give the program a couple of things to do if the threshold has been passed. Now, if I go to examples and blink without delay, or even if I go to examples and blink, since we've worked with that one before, under basics, blink. There's an example of how an if statement is set up. Oh no, it wasn't blink without delay, sorry. Okay, there's an example in blink without delay of how an if statement was set up. So I'm going to copy and paste that here, and then we're going to modify it. So LED state was some variable it had for LED state. Right now, we know what we're calling our output pin already. So we can make our if statement read if the sensor value is less than our alarm threshold, then, with a curly open brackets, then we're going to digital write to output pin high. And if it is not greater than the threshold, digital write output pin low, like that. So general form of an if statement, you've got your stuff that you are comparing in a regular parentheses right after the word if, then it's an open and closed curly brackets containing whatever you're doing in that if statement. Else would go right after it. To make it a little bit cleaner, I'll just put else on a new line like this. And there you have it. If the alarm threshold is crossed, it will write to the digital output pin a high value. So let's see how this works if we upload that. And I'm going to go to the camera view now to see if the lights and everything work. All right, so here's my potentiometer, and I get my hand out of the way. There you go. So now going back to code mode, you should now be able to see the starter DAC. This is about as far as we need to go with a simple potentiometer. We can now view its voltage in real time. We can plot it. We can check to see that the loop is acting at the correct speed. And we can make other actions on the breadboard contingent upon where that potentiometer dial has gone. So now we're going to make things a little bit cooler and replace the potentiometer with the distance sensor that you have in your kit. Let me pull up a PowerPoint presentation real quick to show you what the internal workings of that thing actually are. So if I make this a bit bigger, this is the distance sensor. And I think it didn't come with the kit. I actually just asked people to buy it. But either way, it's an infrared sensor. One of the two little eyes here is an infrared LED. It emits light. And then on the other side is a photodiode. It's a receiver, basically a mini solar panel. And it's basically going to be taking the reflected light from whatever the emitted light is bumped into and then bounced off of. It takes that and turns it back into voltage so that you can read it. The circuit's going to look exactly the same as what we had for the potentiometer. It's just going to be replacing 3 wires. The red one, the bottom wire is the one with the longer rectangle on the bottom of the face of the sensor, but the red wire is going to go to column 40 and over to our +5 volts on the Arduino. The black wire is the middle one. It's going to go to ground. Either of the two is fine. And then finally the yellow wire, the top one, is going to go to column 44, which eventually is going to wind its way over to analog input 0. So let's get that set up in real life here. I'll go to my Arduino cam. I'm going to take the speaker out because I forgot to change the threshold, so every time I unplug something, it's going to scream at me. So I'm taking the potentiometer out and getting the distance sensor. Distance sensor is here. Red wire going into column 40, black wire going into column 42, and the yellow wire going into 44. And then I'm going to just wind this over to the side here like that, so you can kind of see what's going on. And I'll go back to this screen. All right. I'm going to go to the alarm threshold right now and call it 0 so that I can plug that buzzer back in and have it not yelling at us. Since it is currently yelling at us, I will upload the sketch. Okay, so right now, everything should be working about as usual. So I'm going to go to Serial Plotter, and I'm just moving my hand up and down over the Arduino, over the distance sensor. And you can see this trace is going up and down between about 0 volts and about 5 volts. So it's using the full range. I'm going from maybe about 10 centimeters to 30 centimeters. That's about 4 inches to, I don't know, metric is difficult. But kind of a typical range of motion, about an arm length at most. You can see from this trace that there's a lot of noise. That's inherent to the signal and the sensor, and isn't anything that we've done wrong in the circuit. A lot of sensors will have noise like this, and so you can either send this data off to a computer where it's going to be stored, and then you process this out later, or if you want to see a nice smooth trace, we're going to have to do a couple more things to this code. Namely, we're going to smooth this data before we ever see it. That's the next block down in the starter deck. Now, to smooth data requires a couple of things. I'll see if I can get an annotation up here. So first, we need to store a window of the last couple of data points. So if we have an array like this, and at time 1 we get a sensor value, at time 2 we get another sensor value, and we keep going like that. We've got these elements in an array. We need to store an array of this size. Let's just say that that's 50 data points long, for example. And as the void loop is repeating over and over again, we need to fill each element of this array with the next value. So at time 1 we need to fill this, at time 2 we need to fill this, all the way up until we get to the very end. But then at the very end, what we have to do is somehow loop back so that as the void loop keeps iterating, we now start filling this array from the beginning again. If we have that operation within our void loop, what we can do is then take the average of all of this. So if this is array X, we would get the mean of X, and that's going to be a moving average. Every time that the if statement reads true, every time it's been 2 milliseconds, it's going to take the average of the last 50, and that's going to be what we display, and that's going to be what we print. In order to do that, what we have to do is first find a function that makes it possible to loop back, to count from 1 to 50 and then go back to, or count from 0 to 49 and then loop back again. And it turns out there is a function for that, and it's called modulo, or modulo, depending on where you come from, I guess. I'm not really sure where to put the emphasis on that word. I'm going to call it modulo. Anyways, the way that it works looks something like this. I'm going to copy paste from the PowerPoint pretty much, and we'll build this in pieces. So inside the void loop, we're going to be making an index called I increment up by 1 every time a sensor value is read. And so it's going to keep counting 1, 2, 3, 4, 5 all the way up to infinity. This percent sign is going to say divide by something, and that something is going to be the length of the array that we want to keep. In this case, I'm going to make a variable up in the top called smoothing window size, and I'll say that's going to be 50. Once this I equals part here gets to 50, 50 divided by 50 will give us a remainder of 0. And the modulo function is a remainder function. When it gets to 51, it will say 51 divided by 50 gives you a remainder of 0. 52 divided by 50 gives you a remainder of 2. And then it gets up to 100 and it will go back to 0. And then 101 will give you a remainder of 1. So that's going to be the function that allows us to fill 50 data points and then loop back to 0. And every time it does that, we're going to say the smoothing window, that's going to be the array that we're keeping track of and filling. We're going to say that the smoothing window of I is going to equal the current voltage that the sensor value is reading. So that's going to be how we create this moving window. Now I introduced a couple of variables, so let's go up to the top and make a couple of changes before any of the void setup or void loop. And then under smoothing window, we're going to say int I equals 0. That's going to be for modulo. We're also going to make a floating point array called smoothing window or smoothing win. And it's going to be 50 data points long. When I say a square bracket's 50, it's basically filling it with zeros. Those will be overwritten. I'm also going to make a single value that specifies just for general use purposes, and this can even be an integer, smoothing win's size, which is going to be equal to 50. And because I may or may not want to smooth my data, I'm going to give myself a way to tell this program to smooth or not to smooth. So I'll make int add smooth equal 1. And this is going to be like, do you want to smooth? Now, in here, in the smooth data if required, I'm immediately going to know that I need an if statement. So if you want to smooth, it will be if add smooth equals 1, then I'm going to do all the stuff in here to smooth. Now I've got my moving window and I've got my if statement, but the last thing that I need to do is actually average the data in the smoothing window. That's a little bit harder because it turns out Arduino doesn't have a mean function. There's no way to just one word average. So what I have to do is write a for loop. And the for loop is going to be something that for you and for general purpose Arduino programming, if you have an example of a code that you've used a for loop for in the past, you can really just copy paste it and give it new variable names and repurpose it very easily. You don't really need to remember this, but I'll just kind of talk through the syntax here. First, I'm going to need to have a variable that will store a sum that's going to be created. First, to make an average, I need to add every value in an array and then divide by the number of elements. So float temp equals 0 will be my first line, and then for, and then in regular parentheses, I'll say int index equals 0. So from 0, I'm going to make a loop that iterates. When I say index plus plus like that, it indicates that I'm going to be incrementing my index going up by 1. So it'll go 1, 2, 3, 4. And the middle is going to tell me how long to do this for. And I'm going to do it for as long as index is less than my smoothing win size, which is 50. So from 0, keep incrementing up until you finally get to the smoothing window size. And then close the parentheses, open a curly brackets. It closed a curly brackets for me. Well, if I press enter, it did. It closed the curly brackets for me. What I'm going to do in each loop of this for loop is say temp is equal to itself plus the smoothing win of index, like that. So it's going to take the first element of the smoothing window, add it to temp. Then it's going to get the second and add that to temp, and the third and add that to temp, and go all the way up. And now you have the sum, which is, I guess I could have called that sum, but whatever. It's the sum of the array. Now to get the average, you just divide by the number of elements in the array. So the very last line of this is going to be to recast sensor value as temp divided by smoothing when size. And that's the end of the smoothing window. So let's see if that made things a little bit smoother and if I managed to do this without 100,000 typos. So I think smooth when has a capital everywhere. You have to be careful of cases and stuff like that. So there's almost no chances it's going to work first time. We'll see. Yep. Smoothing when size, it says you didn't declare smoothing when size. And in fact, I forgot the ing. Yay. Okay, now it works. All right, so if I go to Tools, Serial Plotter, I now get a nice smooth looking signal. However, it is still in volts. And that's kind of an issue because this is a distance sensor and I'd like it to sense actual distance. It turns out this is actually a pretty easy thing. Usually for a force sensor of unknown origin, you would need to calibrate it by putting weights on it. And for a distance sensor, you would calibrate it by putting it in front of a wall at known distances, and you kind of build up a volts column and a actual known distance column, and you have to create some sort of a function like a linear best fit so that you can convert one to the other. In our case, the sensor company actually provided the calibration. So all I need to do down here to calibrate to physical units is copy paste what I found on the internet, which is a power function. So 29.988 times pow sensor value comma negative 1.173. That's basically saying raise the sensor value to the power negative 1.173. It's kind of a ugly thing, but that's how that works. Multiply this random coefficient by this power thing, and you should be getting centimeters. Let's see if that works. All right. So now I am at roughly 8 centimeters away from this sensor. And if I raise my hand a little bit further and further and further and further, I am now hitting my camera at about 20. If I go a little bit further, I can go up to about 30, and then it starts getting a little bit uglier because it's a light, so it's going to get more messy as a small hand is getting further away. If I get closer, it's very nice looking. Okay, so this is now a smoothed and calibrated distance sensor being plotted in real time at, I think, once every 2 milliseconds. But let's check. We go to the serial print, uncomment those 2 lines, upload again. Now we're going to go to the serial monitor and make sure that the first column is reading 2000 or thereabouts every time. And you can see that it looks pretty good. Every 2000 microseconds, it's producing another value. And because it's zoom, it's killing my computer, but this is actually printing out correctly. Every once in a while, there's 4 milliseconds off. That's really not it. 4 microseconds off, sorry. That's really nothing to worry about for this kind of data acquisition. This is actually working extremely well. Now we have the one last piece of this puzzle, which is to see if we can connect the distance sensor to a physical bit of hardware. And we're going to do that by going up to our alarm threshold that we had previously set to 0. And let's say Well, what would be a good alarm threshold? Well, one way that we can find out what a good alarm threshold would be to see what the minimum reasonable value that I can get from the sensor actually is. So if I comment these two things out and upload the sketch again, I can go to serial plotter and see that I'm actually about 8 centimeters or so, and then when I get closer to the sensor, it's actually going up again. So there's some kind of nonlinear weirdness that's going on below 8 centimeters that's making it impossible for me to get an accurate reading. So let's make 8 be our threshold for an alarm that tells me to not get any closer. And I'll upload this and switch over to the Arduino view. And let's see if I can do this without getting in the way. If I put a pencil over this high enough, nothing happens. I get a little closer. It's sensing that I'm exactly 8 centimeters away. Here. If I can get right in the line of this thing. It's a small pencil, so it reflects poorly sometimes. There we go. And a hand would be like all the time. So, and there you have it, a fully operational data acquisition system that is sampling at 500 hertz, getting distance data, converting it to actual calibrated units of distance, and using that data to trigger a hardware buzzer and light to go off at a specified time and a specified value. Just a couple of final thoughts here. In future projects where you want to use this code as a base, please keep in mind that doing lots of floating point math like smoothing and calibration on a microcontroller before you print that data out to serial and send it elsewhere is not really how people do things. Most of the time, if you're going to be sending the data to a computer for either storage or for display, you send the bare minimum, just that integer between 0 and 1023 per channel, and you let something like Python do the heavy math. That will let you sample at much faster rates. For right now, for one sensor and 500 hertz, it's okay. If you wanted to get 7 channels at 2K, then maybe you would probably have to get a slightly better Arduino, slightly faster processor, slightly better resolution, and only send the absolute bare minimum off to something like Python for actual processing. For the most part, though, going up to at least 500 hertz for 1 or 2 sensors is going to cover almost all of the types of uses that you can imagine being helpful in an everyday life scenario, other than for certain kinds of research. Just about anything that you can sense it makes sense to sense them at 500 hertz or so. And so you have now the ability to do any of that. I would encourage you to go look at some of the other sensors that you have, the photoresistor, the thermistor, it's a temperature sensor. Play with the potentiometer. If that one is a little bit too fiddly, go ahead and go to Amazon and buy a $1 10K potentiometer, just like this one, but bigger. They sell them like big dials and stuff, so they're a little bit more fiddly proof, I guess. This one that they gave you is very, very delicate, and it's hard to keep the wires on it. A lot of the stuff they gave you is very delicate. So you can always replace those parts with more robust things. And also, you can move beyond buzzers and lights. We can discuss motors a little bit more possibly in class. There's a reason I didn't go into them for these asynchronous lectures, but in general, you now have the ability to look up different Arduino projects online and kind of power them through this starter code that I gave you. Just go through, add all of the components. You can follow the instructions in the PowerPoint and follow along with this lecture on video, and you'll have a legitimate data acquisition program. And not a lot of people start there, so that's a good place to be. You can do a lot from here. With that, have a good week.